Hi everyone, welcome back. If you're watching this video, that's because you are in a place in your trig studies where you already learned how to work with the unit circle, how to sketch sinusoids, how to use characteristics of sinusoidal functions to solve a wide range of analytical problems. But now you wonder, well, what else is next? Well, what about real-life applications, aka word problems with trig? There are many situations in nature that behave sinusoidally. And today I have a classic one, a word problem involving a pendulum. Let's take a look. Before we get to that problem, however, I do want to take a few minutes to review a basic concept of geometry, circumference, the circumference of a circle. And then that will lead us to the arc length of a circle. I will explain carefully what that means. So here we have a circle with radius r. I'm going to use lowercase r. I'm going to place a point right here on the circle. And let's say that now I decide, imagine that I'm standing exactly where this point is located. And then I want to go ahead all around the surface of my circle. One complete turn, one complete revolution. If I want to find the entire distance around that circle, that is like finding the perimeter of that circle, right? Perimeter of any shape is the entire distance around the shape. Well, for a circle, instead of using the word perimeter, we use the word circumference. So the circumference of a circle, one complete turn, is the entire distance around. And the formula for that is equal to 2 pi r, 2 pi times the radius. Now, let's say that now I'm not interested in finding the entire circumference of the circle. Let us say that I have this situation here, another circle with radius r, but now I just want the length of this piece of the circle, this piece of the circumference of the circle. Sometimes this red piece of the circle is called the arc. And I want to find the length of that arc. In other words, arc length. So let me even denote that by lowercase l, arc length. I want to find the value of L. Well, now I wouldn't be able to just use this formula because this formula right here is giving you the circumference of the entire circle. I only want this piece of the circle right here. So then what we're going to do is we're going to slightly modify this formula in the following way. Look, if I have this length right here, this piece of the circle, this piece is associated with this angle right here, right? And it's called the central angle. And why central angle? Because the vertex of the angle right here is precisely the center of the circle. So such an angle is called a central angle right here. Let's go ahead and call it theta. So now we're going to start like this. Circumference is equal to 2 pi r. Okay, but now this gives you the circumference of the entire circle. I don't want that. I only want to find L, the arc length of this tiny piece of the circle. So then in order to do that, I'm going to use 2 pi r. But now I'm going to say, well, I don't want the entire one complete turn. And you know that one complete turn is equal to 360 degrees. I only want theta of 360. I only want that particular fraction, the fraction that corresponds to theta of the entire circle. So I only want, and I'm going to multiply this by theta of 360. So this fraction is telling you how much, only how much of the entire circumference you want. I only want this much by that amount. And that is going to give you beautifully now the length of this particular arc, of the red arc of the circle. All that I will do right now is to simplify half of 2 is 1, half of 360 is 180 degrees, and then I'm going to get that L is equal to theta divided by 180 times pi r. And this is the formula that will give you the length of any arc that you may want to get, that you may want to have from that circle, the length of any arc. Notice that if theta is equal to 360 degrees, you're going to have the fraction will be 360 divided by 360, which is 1. So you're left with 2 pi r, which makes sense because 2 pi r is the circumference of the entire circle. Now, what about if theta is being measured in radians, right? And in the case of trig, more often than not, we're measuring our angles in radians. Well, if that's the case, we're just going to follow the same approach, but instead of using 360, I'm going to use 2 pi, right? 2 pi radians is the same as 360 degrees. So then L is going to be equal to theta divided by 2 pi times 2 pi r. So notice how it's practically the same. I'm using the same fraction, just different units. Instead of 360, I'm using 2 pi. And now, when I simplify, 2 pi will divide with this 2 pi on the other part. And I'm going to have that L is equal to theta times r. The formula looks a little bit more simplified when using radians. And it is precisely this formula, the one that we're going to have to use in the pendulum problem. So L equal theta, the central angle, this angle right here, times the radius of the circle. That is equal to the arc length, to the length of any arc that you may want. It can be this big or slightly bigger, no matter what, as long as you know the central angle associated with that arc in the radius of the circle, you can find the length of any arc on that circle. Now on to the pendulum. Let's read the main bulk of the problem, and then we're going to start thinking more carefully. We're going to even look at an illustration in just a few minutes, and then we're going to start answering A and B. So the problem goes like this. The angle H in radians between a pendulum and the vertical may be modeled by a sinusoid in terms of time t. Let's see what that means. So I see my pendulum here, right? So here is my pendulum right here. And this is the vertical that they're talking about, this dotted vertical line. Now, what is H? The angle H in radians between a pendulum and the vertical. So this pendulum is swinging back and forth, just like this. So as it swings like that, this angle is changing, right? It's going to a maximum, but then it changes. It goes to the maximum in the other direction. And I think that this is exactly what the problem is saying, that H is measuring exactly how that angle is changing as the pendulum swings back and forth. Based on the diagram shown, K represents the maximum angle that the pendulum swings from the vertical segment. Again, as the pendulum swings, it reaches a maximum. It doesn't go all the way around. It goes up to a maximum angle, a maximum aperture or opening. Then the angle decreases, gets to 0 at the vertical right here, and then it starts opening again in the other direction, and it reaches a maximum. I mean, it's going to go up to somewhere here, and then it goes back to that maximum, and so forth. So K is the maximum angle reached by the pendulum on either side of the vertical. The period of the pendulum may be approximated by this formula. So this is going to give us the period of the pendulum, where L, this is uppercase L, is the pendulum's length. So this is right here. I'm going to even write that down. This 20, let me use a pen. This 20 here is equal to L, and G is the acceleration due to gravity. This is 9.8 meters per second squared. So now A is asking us to find a sinusoidal expression that is going to model the situation. And then we're going to go ahead and sketch a piece of the graph from 0 to 5. But before we even get to that, I know that some of us may be wondering, how can the motion of a pendulum be described by a sinusoid? Sometimes that's the tricky part. That's the part that is difficult for us to capture. How can just a simple motion of a pendulum that swings back and forth be captured by a sinusoid? And I have an illustration for that. I want you to see exactly how that's possible. Let's take a look. Okay, so if you notice right here, this is the pendulum. Again, this is where it is attached. And this is the vertical dotted line. And the pendulum will do its thing. It's going to swing back and forth. And then you're going to see how the sinusoid comes alive. There, if you notice. Let's just observe what is happening. Notice that when the pendulum goes all the way to the right, the sinusoid is above the vertical. Then when it goes all the way down to the left, the sinusoid is below the vertical. Right? So down, up in one direction, and that's how it keeps the motion going. So when it gets to the maximum here, we are above. When it goes to the minimum, we are below the vertical. But you really see the lovely sinusoidal motion. You see the sinusoid in action, how the pendulum, the motion of the pendulum is generating this very nice sinusoid. And what we're going to have to do very soon is to determine the equation of this particular sinusoid. And you know that we can do that in various ways. We can determine the expression in terms of sine and in terms of cosine. We're going to try to go for the easiest approach in this case. Here is the same problem written down, just a little bit smaller. We're going to use the right side over here to start thinking through and extracting all the math from all those words in there. Notice how I have a picture right here of the motion that we just saw. And let's see, So what I did here was I came and I turned the picture around. If you remember in the illustration, this dotted was not horizontal. It was actually vertical, just like this one on the left. But here, I want you to see that if we just do a rotation, then the vertical becomes horizontal. And now we get a better appreciation of a typical sinusoidal wave, where part of it is above the horizontal and the other part, symmetrically, is below the horizontal. That's why I turned it around. I rotated the picture. Okay, so how do we start here? We're going to have to go ahead and begin by writing the general form of a sinusoidal function. And I feel that in this case, it will be easier to use a cosine graph. So I'm going to start with h of t equals a times cosine b t minus c plus d. So please know that as I write this expression here on the screen, I am already assuming that you have a basic knowledge of the general form of a sinusoidal function and that you also know about transformations. I have another video on the channel that talks a little bit more carefully about transformations of trig functions. So I'm going to make sure to link that video below in case you want to take a look. But there are a few things. Actually, there's going to be a lot that I will already assume in this video. All right, so here is what we have, and I'm going to use cosine because I believe that in this case it's going to be a lot simpler to go with a cosine expression rather than a sine expression. Now, things that I will have to find, I'm going to have to settle on the value of A, the value of B, C, and D. Now, let me start with D, for instance. So D is your vertical shift. You may remember that D takes the original parent function and it shifts that function up or down. So it's a vertical shift up by D units. But now, in this case, do I need a vertical shift? Look, the motion of this pendulum, it's up and down, just like this, just like we saw in the illustration, right? Well, in the illustration, it was from right to left. Here, based on the rotation of the diagram, we're going to go up and down, and it keeps going like that. And it's always with respect to this dotted horizontal line. The entire sinusoid right now is symmetric to that horizontal line. The beginning of the sinusoid, even though it doesn't look like this here, but this red dot should really be right here. Just like you see here on this picture. You see the red dot right at the center of everything. So then, because the motion is already nicely symmetric to this horizontal line, there is really no need for D. We don't have to lift the graph up or down. The motion is already nicely symmetric with respect to this horizontal dotted line. And then the center of the pendulum is right here sitting on the horizontal dotted line. So there is no need to have a vertical shift whatsoever. So in this case, I am going to make D equal to 0. Now, do we need this C? If you remember, C signals a horizontal shift to the right or to the left. Now, in this case, do I need that? Look, again, here is this red dot. I'm going to go to the picture on the left. It's right in the center. And the motion of the pendulum, it's with respect to this center over here, right? As the pendulum swings back and forth, it is always attached to this red dot. Now I'm going to transition to this picture right here. The red dot is right here, right in the center. And if you notice that as the pendulum swings back and forth, it is always fixed at that point. So then the sinusoid doesn't shift to the right or to the left. The motion is always somehow with respect to this pivot right here. Maybe it's better to call it a pivot. So in this case, there is no need also to have a horizontal shift. So I'm going to make this C here equals to 0. So then this is what I have. I have that the h of t expression that I am after should be equal to A times cosine B times t. And there is going to be a B. B is not just going to simply be 1 because B, if you remember, depends on the period. And the period is this expression. It's not just 2 pi. It is 2 pi times the square root of L over G. So B is going to be affected by that expression. And then A as well. We're going to have to go ahead and find A. Okay, so how do we do these things? Let's see. Let's start with B. I think it's easier given that it's completely determined by the period. So the period was given to us as 2 pi times the square root of L divided by G. We know precisely what is, you know what? I think I used the wrong L. This should be uppercase L. So let me fix that, uppercase L. Okay, so 2 pi square root, and then L here is the length of the pendulum. That means 20, and G is 9.8. Then when you get your calculator and you divide 20 divided by 9.8, you're going to get a decimal. But it actually is a decimal that can be expressed by a nice fraction. So I can write this as 2 pi square root over 100 over 49. Now you don't have to do that. If you want to leave this number in the whole radical as a decimal, you can. But in case you have to give fractions, I want to show you how to do that. 100 divided by 49 is the same number as 20 divided by 9.8. And you can quickly take a look with your calculator. You can convince yourself that this is correct. So now we're going to get here 2 pi times the square root of 100 is 10, and the square root of 49 is 7. And now we can simplify this as 20 pi divided by 7. So that will be equal to 20 pi divided by 7. So then that becomes nicely the period. So now that I have the period, I know that B is equal to 2 pi divided by the period. That means that we're going to have 2 pi divided by 20 pi over 7, which is going to give us 2 pi times 7 over 20 pi. And now simplifying, pi's will divide each other out. Half of 2 is 1, half of 20 is 10. So then this will be equal to 7 divided by 10. So that becomes B. Great. That means that we already have the value of B, 7 over 10. Now though, we're going to have to go ahead and find the value of A, the leading coefficient. A is very much connected to the amplitude of the function. If you remember, the amplitude of a sinusoidal function is equal to the distance between the maximum value to the axis of symmetry. Now, because I got this screenshot from the illustration that we were watching, it seems as if the sinusoid is such that the maximum value changes. You know very well that this is not the case. This was an effect of the illustration. In reality, sinusoids always maintain the same height above the axis and below the axis. So always the same height. So the amplitude is always the same no matter what. It is the distance from the highest point on the graph to the midline, the axis of symmetry. So in this particular case, amplitude is the greatest distance from the axis of symmetry. That pretty much relates to the value of K. If you remember, K is the maximum angle that is formed when this pendulum is taken all the way to the right, the maximum stretch of that pendulum. And then when you let it go from the maximum, then it starts swinging, but it always goes to a maximum, then on the other direction, the same K, and so forth. So K pretty much is the amplitude. I'm going to write that here, that K, the value of K, will be the value of the amplitude. Well, how do we find K? So what we're going to do, we're going to use the idea, in particular the formula that we developed for the arc length, if you remember in the review that we had at the beginning of this lesson. So I'm going to go ahead and redraw this piece over here, because I want you to pretend that we now have a circle with center right here at this red dot. Imagine that you have a huge circle. I'm just not going to draw it out. It's just going to get too large. But I'm going to draw a piece of it here. So here is the center, that red dot. In fact, I can make it red as well, just like this. And then we're going to have a circle that is going to go around. So here is the vertical dotted line right here. This is the length of the pendulum. The length of the pendulum will be 20, like they told us, and it will turn into the radius of that circle. Now, you may remember that in the review, this was the central angle and we were using theta. But now we're going to use K instead of theta because they have chosen the variables. That's totally okay. So then this is going to be K. And then something else that they nicely gave us was the length of the arc, lowercase l, the arc length. So they gave us this length over here that I'm tracing in red. This is precisely 8 centimeters. So then now I know that L, if you remember, is equal to R times theta. This is using the variables that we were using in the review. Now I'm going to switch and I'm going to start substituting the new variables and the values that I have. So for example, notice how here 8 is lowercase l. So I'm going to put 8. R is 20. And then instead of theta, we're going to write k. So then we're going to have that k is equal to 8 divided by 20. And now we're going to simplify. 4 goes into 8 twice and into 20 5 times. So then we're going to have that k is equal to 2 over 5. So beautifully, we found the amplitude right here. So now we're almost there with the expression. But let's see, how do we start? Are we going to let a be positive 2/5 or will a be minus 2/5? In other words, if you remember, again, positive versus negative, that indicates do we do a reflection about the axis of symmetry or not. If we don't do a reflection, A is identical to the amplitude. If we do a reflection, A is going to be minus the amplitude. Again, I'm already assuming that you feel quite comfortable with the whole idea of reflections. How do we tell if a reflection is needed or not? Look, let's go back to the beginning of the problem. The angle h in radians between the pendulum and the vertical may be modeled by the sinusoid. Okay, but here, it is precisely here. I'm going to go ahead and see if I can highlight. Based on that diagram shown, K represents the maximum angle that the pendulum swings from the vertical. So that phrase there is telling us that in order to initiate the swing, they took the pendulum, they took it from the rest position, and they brought it all the way to the maximum, all the way. So you pull it all the way to the maximum, and then you let it go so that the motion starts back and forth, back and forth, back and forth. So we are starting exactly at time equals 0. We are starting at the maximum. And this is how parent function cosine behave. Parent function cosine at 0 is at a maximum. And that means that no reflection is needed, which means that A will be identical to K, to the amplitude. So here, the expression will now be like this. H of t will equal to 2 over 5 times cosine, and then if you remember, B was 7 over 10 times t, and that becomes the expression of the sinusoid. Now, the second part of part A was to sketch the piece of the sinusoid that is within the domain restriction of t from 0 to 5. So we're going to go ahead and do that. That shouldn't be difficult. And we're going to start with the process that I illustrated in another video in this channel. Again, I will link that below for you to check out if you want to. I'm going to go ahead there and follow the approach where I take the period and we consider a fourth of the period. So in this case, if you remember from the previous discussion, the period was equal to 20 pi divided by 7. But now, because we are going to be sketching, it will be helpful to approximate that as a decimal. And as a decimal, this is approximately 8.976. Now, following the process, I'm going to go ahead and consider 1/4 of the period. And again, in the video that I'm linking, I explain exactly why we're going to do 1/4 of the period. So there's no need to repeat that here. 1/4 of the period will be 1/4 times 8.976, which is equal to 2.244. So now we're going to start finding the t values. So we're going to start with t sub 0. T sub 0, right? Since we are not doing a horizontal shift at all, t sub 0 will be equal to 0. Then t sub 1 will be equal to 0 plus 1/4 of the period, 2.244. That's going to give us 2.244. Then t sub 2 will be 2.244, the previous t value, plus 1/4 of the period, 2.244. This will give us 4.488. And then that's already getting quite close to 5. If we compute t sub 3, we're going to have 4.488 plus 1/4 of the period, 2.244, and this is clear that this will be bigger than 5. So we're not going to be plotting t sub 3. We're just going to plot these 3 t values right there. So up to t sub 2. We're not going to plot this one here. Okay, so plotting those points, at 0, we are at the maximum. I'm going to put a dot right here. Then t sub 1 is about 2.2. I'm going to round it even further. So 2.2 will be, let's say, somewhere here, and I will already be on the axis. The next one will be at the lowest point of the sinusoid. That's going to be t sub 2, which is approximately 4.488. So very close to 4.5, but not exactly, just a little bit towards there, towards here. So that is going to take me to the lowest point right there. Okay, but because they did include 5, if you notice right here in the domain restriction, I'm going to go ahead and I'm going to find the y value that corresponds to t equals 5. In other words, I'm going to find h of 5. I already have the model. So h of 5 will be equal to 2/5 times the cosine of 7/10 times t, but now t is 5, so times 5. When you enter all that in the calculator, you're going to get minus 0.37. So when t is 5, we're going to be really close to negative 0.4, but not exactly at negative 0.4. All right, so plotting that point, we're going to go ahead and put it somewhere here. So then now joining the points that we have with a smooth curve, and sometimes this is the challenging part, especially with points that are so spread out. Let me try that again. Right here. It doesn't have to be perfect, but make sure that you try to follow your curves as much as possible. We're going to go there. So here is one point, here is the other one, the one on the axis, and the one that we started with. Okay. Just trying to erase this part right there. All right, so here is the graph between 0 and 5, exactly as they asked for. Now part B is asking us to determine the position of the pendulum after 6 seconds. They want us to express the answer to the nearest tenth of a centimeter. But first, let's do the first part. They're giving us time. They're telling us that t is equal to 6. And they're asking us to find h of 6. It's like giving you the input. We have the input, which is 6, and they want us to find the output, the y value. In this case, the value of h at 6. So for that, we're going to use the model. We know that h of t is equal to 2/5 times the cosine of 7/10 times t. Now we're going to substitute 6 into t. So then that means 2/5 times cosine 7/10 times 6. And now you're going to get your calculator and you're going to input all of these values. Just make sure that your calculator is in radian mode. And when you do that, you're going to find that h of 6 is approximately equal to minus 0.196. Now, the units here are very important. Remember that h is modeling the angle that is formed as the pendulum swings back and forth. The maximum value is k, if you remember, but then as the pendulum swings back and forth, h is changing. So in this particular case, the units of this decimal is radians. So I'm going to write radians here. However, this part here, notice this part right there. Let me even highlight it. This part right here is asking us to express the answer to the nearest tenth of a centimeter. Centimeters. They don't want radians. They don't want radians. We're going to have to go ahead and change that to centimeters. So then, remember the connection to arc length. So here is the vertical. Right, that's the vertical. Now the angle that we're dealing with is negative, so I'm going to go ahead and position it here on the left. But now, if I'm thinking from the point of view of a circle, I don't care about negative or positive. So in this particular case, I'm just going to use 0.196 for the central angle. So this central angle here will be 0.196. I'm going to look at this purely geometrically. So I don't care here about positive or negative. Again, this is where the pendulum is. And as the pendulum swings, this amount in terms of theta, it creates this red arc right here. Again, this theta corresponds to this arc. This angle corresponds to this arc right here. So if I want to go from radians to centimeters, I am going to give the length of this arc that corresponds to this angle. The length of this arc. So I want the arc length. Remember that we were calling that lowercase l back in the introduction, in the review that we did at the beginning of this video. And there we said that L is equal to R times theta, the central angle. We can keep calling it theta, or we can call it H. In this case, it is H, but you know what? I'm going to keep it simple. Right now, this is my angle. Okay. So also, we don't care about the negative because length is always positive anyway. So drop the negative, keep everything positive. Length is positive anyways. So L is going to be, the radius doesn't change, it's the length of the pendulum. If you remember, 20 and 20. So we're going to have 20 times 0.196. And then that will give us, if we multiply that, we're going to have approximately 3.9 3.9 centimeters. And this is exactly what they asked for. All right, everybody, I hope that you found this video helpful. This was a very challenging problem. It required a lot of information, a lot of thinking. There were many concepts linked together, which is what I think is so wonderful, how it connects very high ideas of trigonometry to something simple as circumference and arc length. So I'm really hoping that you enjoyed that. You can rewatch the video until you feel that you have a good handle of it. In the near future, I'm going to bring another application. I have a few other ideas for you, and I'm hoping that you will also find those applications helpful. Remember though, practice, consistent practice is the key here to be able to do these problems quickly and accurately. Anyways, if you have any ideas in the future of problems that you would like me to solve, just comment below and let me know exactly what you have in mind. In the meantime, have a great day. See you next time. Bye.